Okay. Oh, crystal clear audio. Even if the lingo isn't. Hey, that's for our class. Maybe it applies more than ever. Okay, so I need to bring in the data because I see my environment is empty because I closed up last time. I closed up shops. So I'll just bring in the iris data set. Well, the iris data set is there already, but I'm going to bring in these libraries here. I need the ggplot, I need the dplyr, and I need ggfortify, which I suspect is for that WSS plot. So what we did, or what we kind of thought was a good plan, is what if we have three categories that we know are distinct, and we try to make clusters and see if our clusters are close. So we're going to remove the species data, the species information temporarily from that iris data set. So we have 3 species of irises, so flowers. It's really boring data. It's like sepal width, petal width, something that I don't know what it is. It doesn't matter. It's just a nice data set to work with for examples. So without kind of going into what the WSS plot is doing, making it dangerous, just run it, see what happens. No, but you can go through and you can pick it apart. But when we ran it, and maybe, oh, I need to actually tell it to give me the plot, right? So then when we ran it, we saw that, okay, 2 clusters seems like it would be better than 1. So that's good, right? Because we've got this decrease in variability within each of the clusters. So of course, one cluster is basically just everyone is together and no one is essentially in a cluster. Seems kind of weird, but that's how I think of it. So that's where you're going to see the most variability within that one cluster. So then as soon as we go to 2 clusters, we decrease that variability so that we decrease the differences within each cluster. And then you can see that it decreases as we move through the number of clusters. But once we hit 4, right, you can see that there's not real improvement here. Going and looking at 10 different clusters is not that different in variability within the clusters from, let's say, 4 clusters. So you usually want to stick to as few clusters as you can, because in your analyses, you're going to have to talk about each of these clusters. And so you don't want to have to talk about 10 different clusters when they're all, relatively the same. So, so the fewer clusters is typically better, but it depends on your analyses, what you want to do. So first thing we're going to do is we're going to look at what is 2 clusters going to do for us, right? And then we're going to look at 3 clusters. Now we happen to know that there should be 3 clusters. So the 3 clusters should be better, but how do we decide if it's better? And it is all subjective. So it's really hard to draw a hard line at what is better. But that's going to be up to you in to argue in your reports. Oh yeah, so then we first consider clustering with k equals 2. And so there's a KMeans function, okay? And it just takes the data and we tell it how many clusters we want. I'm going to save it in something called KMean. And so, but if you just run the KMeans of the data at 2, you can see it generates all this information. So that needs to be stored somewhere. So we've got the cluster means. We've got a cluster vector, right? Looks like the this is like one of those things that my grandma posts on Facebook. It's like, can you spot the one? And it's a bunch of sevens. And there's like a one somewhere. It's like, I did. Okay, cool. So 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, cluster 2, cluster 2, cluster 1. Here's a cluster 2 again, right? But then mostly cluster 1, cluster 2, cluster 2. So we can see, and then we can map that back to the data set, and then we could see who's in what cluster. So then, of course, it calculates, I shouldn't say of course, then it calculates the within cluster sum of squares. That's going to be a measure of variability. We don't need to worry too much about it, right? But, and then it has a list of all these available components. So if we name it something like here, I've just ran the bare code, but if I save it in something like KMean, what this means, the available components says that there's a KMean $ cluster, there's a KMean $ centers, there's a KMean $ tots, no, total SS, KMean $ within SS. So we can access each of these pieces of information individually if we want to, but it means we have to save it or assign it to a name. Right, and so that's what I'm going to do here. I'm going to call it KMean. So when I run this, it has that same information over here that we just saw when we ran it bare bones. Okay, so now if I have a look at the centers, cluster 1 has developed a center for the sepal length, the sepal width, the petal length, the petal width. And don't worry, you don't have to know what those are. That's kind of irrelevant, but so that's just one way that you could access some of that information that's generated by using the KMeans command. So there's an autoplot which requires the name of the KMeans command. So wherever you've stored that KMeans command, you can autoplot it. Okay. It also has to know what the original data was. Frame equals true, I think, is what kind of frames in the cluster. And then frame type equals T. I can't remember what the T stands for, but there's a couple of different options, but it's probably a solid line or something. So let's see here. So we can use this autoplot, and it plots all the original data points, but it also gives a color by cluster. Now we could have done this kind of by hand, right? We could have added our cluster information to our data set, and then we could have built a scatter plot where we, what's the word I'm looking for? Facet by the cluster, right? We could have done that. We could have generated something like this, but it's just nice to have that autoplot. So you don't need to use autoplot, but it's just nice and handy to have. So now, right, there seems to be kind of some information. So notice how the circle is just kind of around most of the data. There is some pink data over here, or red, or whatever this color is. That's kind of borderline with the turquoise, and we're kind of missing some over here, right? But they're still they're assigned to a cluster. They're assigned to their closest cluster. But let's see if we can get some better clustering with K equals 3. So we do the same thing again. So I'm just gonna go through here. You can see that now I have 3 clusters, of course, because I told it to. And when I look at the centers, then there's some slight adjustments here, right? One's at 5, one's at 5.9, one's at 6.85 for the first column, for example. And so that's not really information that we need, but it's nice to have and nice to know how to access it, right? So if we auto plot this guy, now we see what 3 clusters would look like. Notice that there's some overlap here, but it looks like, you know, the red guys are over to the right and the blue guys are over to the left, right? But their centers are relatively close. But we were able to distinguish between the two. So like I said, one of the things that we could do is we could generate these clusters, and then we can look at, we can add the cluster information. So what cluster was it assigned to? We lose everything else except for, so we lose the center information, we lose everything unless we add it on, but we don't really need it once we have the clusters. But to add the cluster information, you can use the Cbind, which is a column bind. So now you're just adding on another column to the data, right? And so you could go on and you could add other information here, but usually the cluster is all you need. And I'm overwriting the data command with this new data, right? So now I'm updating the data. And sometimes you might not want to do that. You could call it data 2 or something like that. Okay, maybe that's cleaner. Otherwise it gets confusing maybe. I'll show you what it looks like if I run just this bare code chunk using the Cbind. Scroll up here. This is the stuff no one wants to see, the actual data. Oh. So it's got the data set, it's missing the species, so we could tack it on to the iris data set, right? You'd want to make sure that you haven't mixed up the original data. We haven't in this case, so just binding it onto the iris data set would be fine as well. But here the KMean $ cluster tells me which cluster everyone's in. Hey, this little guy's in cluster 1, just out of nowhere. Anyways, we can, oh, it's because I haven't called data 2. Now it knows what data 2 is, right? And so here's the head of the data, which is a nice command if you want to show the general structure of your data. And you can tell it to do more than the first, I guess, 6 rows by adjusting it, but that's okay. That's usually more than enough to see what's going on. Good. Okay. So after class, I'll post the updated code. It just has a little data two, just to differentiate between the 2 data sets. But besides that, I think you're good to go there. Oh, I guess haven't been keeping an eye on the chat, but it's crickets on the chat. That's probably good because I wasn't looking. That was your chance. So I'm going to stop sharing here. And you guessed it. You will have a clustering assignment. I didn't quite get it together before class, but I'll post it after class, and then we'll make it due November 5th. November sounds like a long time from now, right? It is and it isn't. I know, crazy. So let me just get this iPad going here. Oh. I'm glad you feel like the semester is almost over. It's going by really quickly. It's making me nervous, but I mean, we're staying on top of things. I don't know what else we can do, but yeah. Yeah. It's what do they call it? Death by 1,000 paper cuts. All your assignments are due on November 7th, huh? Okay. I was thinking the Friday, so you wouldn't have to think about it on the weekend, but maybe that's when you need to work on stuff. Oh, so the final presentation, it's going to be a recording, and I have a couple of ideas up my sleeve. Let me bring up, sorry, before I will keep talking about that. I'm just going to bring up, share this screen, start. Okay, rocking and rolling now. Oh, come on. Okay, let me just adjust this here. Otherwise, I might forget. 300. Okay, so okay, so the final project is basically going to be like all the assignments that you've worked on, but all together. Okay, so you're going to draw on all the things that you've practiced in the assignments. Now, there is a presentation that you have to do, but it's going to be a recording. So I'll chat with Joe, but I think he just has it available so you could work on it and you can submit it until, when's the last day of finals? I'll have to chat with Joe to confirm when it's due, but it'll be in the final exam time, and I'll make it kind of towards the end. You'll be really tired by that time, so maybe don't put it off until then. But yeah, so I'll have to confirm, but it'll be due in the final exam period, which is when? Well, it is from the I want to say until the 21st or something. Yeah, so I want to have your first mini presentation. And one thing I was thinking about was that because you have that feedback from the first assignment that you did. So one thing that I think would be really good is if I give you one that's similar, but we have to do a presentation with it, right? Because I posted that code that I did, and so you'll have a lot more to draw on, and then we can really solidify those things, and you'll do a presentation on that assignment. Sounds like there's 2 assignments coming at you, but I'll make the other one due a little bit later. So let's see here. I will post an assignment for chapter 5. Now that we've finished and we've seen all of it, nice. Then we can do an assignment here. So I'll post an assignment for chapter 5, and it will be due. When did I say? Well, let me know in the chat. Do you want it to be due on the Friday or on the Sunday? Friday, November 5th or Sunday, November 7th? Sunday. Everyone wants Sunday. You guys don't want to have it all done by Friday and then not have to think about it for the weekend. That's okay. All right. How about will be due Sunday, November 7th at 11:59. That's the same as always. Okay. So then your first presentation assignment will also be posted, but will not be due until November 12th. Pretty sure. Yeah. Yeah. So it's going to be, I encourage you to work on it, of course, before then, because it's going to be pretty similar to the assignment that you handed in. You've already got feedback on. And so, so that'll be good. But I just don't want to crowd you guys. So I'm giving you lots of time to do these, but I know you guys are all busy, so that's why. Okay. And so, okay, good. So you'll have a presentation. So then you'll have an idea of what to expect for that final presentation. So just as a note, because we're talking about it, let's just, the final presentation will draw on concepts from all the previous assignments, or most of the previous assignments. Concepts from all/most, depending on what you want to do, from all the previous assignments. And will require a video presentation. So you don't have to do a live presentation, because that can be really scary, really intimidating. So you do get to do a video presentation where you upload a video. Same thing with the other presentation, where you basically walk me through your report. Okay, so the previous assignments and will require a video presentation. It will be due during the final exam period. Which I can't really remember. I think it might be the 21st, but not sure. It's kind of the end of the final exam period. Okay. But by that time, you want to be off. You want to be done. But anyways, so lots of stuff going on. Was there anything else that I was meaning to say or do, or can't remember? Seems like a lot. All right, then I can't think of anything else. So it's you've got creative license. So so all the expectations and things like that will be in the instructions for the report. So when I post this, the presentation assignment, it'll have criteria for the presentation. Now, one thing that I want you to keep in mind is that it's about 5 minutes that you should be aiming for, probably less than 5 minutes, because we're not going through a lot of information here. So, so really what you're practicing with the presentation is, yes, of course, public speaking, it's scary, blah, blah, blah. But also, are you able to condense information? Are you able to pull out the most important things that you found so that you can deliver them in 5 minutes? You pretty much don't have time to say anything in 5 minutes. Pretty sure I've been talking about this for more than 5 minutes, right? So 5 minutes is not a long time. So that's a skill too, being able to condense it. Think about it as kind of like an elevator pitch, right? Oh, here's what we found, and here's how you can make more money. Okay, bye, right? And so how you do it is completely up to you. I obviously like this format. I mean, we're restricted to being online. If you wanted to set up, you know, some sort of camera, do a proof of life video, no, right, like have a camera and maybe show your screen. I don't know. So you can get creative if you want to, or be like me and you can be in Zoom alone and just share your screen and talk about it, and that works too, right? And so you can kind of do whatever you want to convey this information, but as long as what you are presenting is something that you would be okay presenting to your boss, right? And so that's the whole idea. So I know that's hard to do, right? How am I supposed to do this, right? But you can always spitball ideas with me, and we can figure something out. Okay. Okay. I think that's, well, now that I've overloaded you with assignments, let's talk about something else. Change the subject. How about that? Whoa. For chapter 6, so chapter 6 is on statistical inference, and for if you've taken, you know, something like Stat 230, this will all be review. Okay, if you're taking Stat 230 with me now, we will go into it in more detail, but this is just kind of an overview, and I was trying to keep it as printable as I could. And so I think I got it down to 5 pages, but it did require a little bit of finagling. So anyways, see how it goes. There's a lot of information here. There's a lot of terminology in inference. There's a lot of ins and outs. You might remember. So when we say inference, what we mean is we mean things like confidence intervals and hypothesis testing. And you might remember p-values, or we haven't quite got there yet in Stat 230. So we'll kind of try to balance the keel here. Okay. So first thing we need to do is we need to talk about, so the reason we're covering this is not because I need you to be able to make a confidence interval for anything, or because I need you to do these calculations by hand. No, that's not what we're doing. But when you're out in real life and you've paid someone to make a report potentially, then you should probably know how to read that statistical jargon, right? A little bit, feel a little bit comfortable. And so that's what we're doing here, kind of knowing the ins and outs. And here we go. All right. So there's a lot of text here, and I apologize. Oh. Bring this in, why not? Put it on a fresh page even. No, I won't. Put it on a fresh page. Maybe I should have. Okay. So it all starts with collecting data. Okay. So there are a lot of things that we need to remember and to keep in mind when we're collecting data. And so the main thing is that our sample, so whatever sample information that we have, our sample has to be representative of the population that we're trying to talk about, right? And so of course, the easiest way to do that, but also the most impossible in most scenarios, is to collect a census. So a census is when we have information from every element in the population. Okay, and so if you're accessing everyone in the population that you're interested in, right, doesn't have to be everyone, but that you're interested in for your study, then you have a census. That's never going to happen. You're never going to have a census. I'm pretty sure even the StatsCan census isn't really a census, because I'm sure people don't reply. Even though it's the law, I'm pretty sure, but people don't. So even the census isn't necessarily a census. Right, so, but what we're trying to do is we're trying to take sample information, right, and say that, well, if we have a good enough sample, then we could learn about the population without having to collect information on the entire population. Okay, and so what we're doing for inference, oh, and I see I have a page break there. For inference is we take information from a sample to learn about the population. So, but we don't want to be having to look at the entire population. So we take information from a sample to learn about the population without having to sample or without having to collect information from the entire population. Collect information from the entire population. Yeah. Okay. So there are kind of taking a census is usually almost impossible, but even if it is possible, like if we're restricted to all Canadians, that's still really hard to do, right? So you can see how we don't really want to collect the entire population every time we want to learn something new. Even if we're in kind of a production setting, we're looking at, you know, the average weight of cereal boxes in a certain amount of time. You could look at those cereal boxes at that certain amount of time. You could look at all of them that you're producing, that you're filling, or whatever. Usually we talk about, you know, filling cereal boxes. You know how they have those machines that like fill it with a certain amount, and it's supposed to be a certain amount, whatever is printed on the box, but then sometimes we know it's overfilled, sometimes it's underfilled, so we have to deal with that. And so sometimes it's possible to look at the entire population, but we still don't want to, and sometimes it's just flat out impossible, right? What if we want to look at So not just the cereal boxes that are filled in a certain time frame at a certain factory, maybe. What if we just want to look at all the cereal boxes that are coming out of this factory? So that's past, present, future boxes, and we can't do that, right? And we don't want to do that. We don't need to do that. And so that's where statistics comes in, statistical inference, and that's why you need to take statistics. But at its core, for most problems, especially problems that we'll have to deal with, we're either going to deal with a means problem or a proportion problem, okay? And so we need to be able to identify, okay, is this data from a mean situation? So talking about the average, so that's going to be from quantitative data or numerical data, right? Or is this going to be a proportion? So a proportion is from categorical data, because there's going to be some proportion in each category. So I've got this little example here, but I'll hold off on talking about that and just outline. So most analyses, now we can talk about other things, but most things, unless you're doing really advanced stuff, most analyses can be broken into a means question or a proportion question. Most analyses can be broken down into a means or an average, I'll say, or a proportion question. Okay. So if you're talking about the average, then remember, this is if you have quantitative data. Quantitative, / numerical data. Those slashes don't really correspond, but I think you know what I mean at this point. So quantitative or numerical data, however you want to describe it, versus a proportion is going to be for categorical data, or qualitative if you prefer, categorical. And maybe I'll do that. Qualitative / categorical data. Okay, so the question that we want to answer is going to fall into one of these two categories most of the time, right? I would say all of the time. That's how I know that these are basically the only ones that you're going to do. But I mean, who am I to say? Maybe you'll go on and do some crazy advanced stuff. Who am I to say? You know what I'll do here? Crop. I'm going to crop top this. Then I'm going to bump this up. Sorry, guys. Hey, I want to shrink it up. There. So if we read these two scenarios and we have to classify them as either a proportion question or a means question, then there's going to be some key information that we're going to notice. Okay, so I'll zoom in here a little bit, make it as big as I can. So members of a particular party in Texas are considering giving their support to a particular candidate for election to the US Senate. The party leaders want to estimate the proportion. Well, that sounds like a keyword. Of registered voters in the state that favor the candidate. A sample of 400 registered voters in Texas is selected, and 160 of those voters indicate a preference for the candidates. So the estimate of the proportion of the population is going to be 160 over 400, which is 40% or 0.4 from the sample, right? And so here, this is, of course, a proportion question. But even if it didn't have that information, so here they use the word proportion, and often it's hard to get away from using the word. So that's a really good thing to keep an eye out for. But they've also followed it up with thus an estimate of the proportion of the population. So here they've used the word proportion to kind of nudge us along here. But what's another reason that it's a proportion? Because would you vote for this? Do you favor this candidate? Yes or no, right? That's going to be a categorical variable, right? So everyone answers yes or no, yes or no, yes or no. And we don't know how many options there were, but the only responses that we're interested in are the yeses, right? Would you vote in favor of this person, whoever it is? So since I'm trying to summarize what the variable would be called, since the in favor variable is categorical. So we only care about one of those categories. So all the other ones would be lumped into a no, whether they're no's or undecideds or whatever's, it doesn't really matter because we're only concerned with those who said yes, they would support that candidate. So if we look at the next one, a tire manufacturer is considering production of a new tire designed to provide an increase in lifetime mileage over the firm's current line of tires. To estimate the mean useful life of the new tires, the manufacturer produced a sample of 120 tires for testing. The test results provided a sample mean of 36,500 miles. Hence, an estimate of the mean useful life for the population of new tires is 36,500. Now, again, they have gone ahead and used the word. Like I said, it's hard to formulate a research question without using the words mean or proportion as appropriate. So that's kind of a good clue here. But this is going to be a mean question because the useful life of the new tires, so the life variable, right, is numerical, right, or it's quantitative because it's some count in miles, right? It's some measurement in miles. So it's a mean since and I'll put kind of quotes around, since life is a measurement, which means it is quantitative. Okay, so how we deal with these are going to be a little bit different, right? Proportions behave in a different way than means do, but the framework that we deal with them in is all the same, right? So inference, regardless of what scenario you're talking about, is going to be the same, and that's really nice. So we'll talk about that, talk about the general framework, And then we'll look at the two options. If you've already taken a stats course, then you know that there are more questions than these that we could answer, right? We could compare two proportions. We can compare two means. We can compare multiple means with ANOVAs, and so on and so forth. So there's lots of different things that we can do, but at its core, there are really proportion questions or means questions, and then we just go from there. Okay. So some of the terms that we are going to be using are things like, of course, the sampled population. Now, that's exactly what it sounds like. It's the population that we drew the sample from. Okay. The frame is the list of elements that we pulled our sample from. Okay. So in the first example, so that this one here, the political party one, which is a proportion question, the sample proportion is all registered voters in Texas, and the frame is a list of all the registered voters. So they're going to be similar, right? But where are you pulling your information from? That's your frame. And then the population that you're trying to sample from, that's your sampled population, but they're very, very similar. So the sampled population for the tire mileage example is a little bit trickier because the sample of 120 tires. So they said, okay, we produced this great new tire. Let's go make some up, I guess, and test them out to make sure that they're actually better than what we already have. And so this is from just a brief moment in time, right? The 120 tires, they were all produced basically at the same time, but we're trying to talk about all of the tires of this type, right? And so we can think of the sampled population as the conceptual population of all the tires that could have been made by the production process at that particular point in time. So it's kind of, so the sampled population is more of an idea, whereas the frame is the actual list that you have to draw from. Okay. So we'll start talking about the differences in selecting a sample. Oh, that's what I wanted to say. So if we're looking, so in our conceptual kind of sampled population, right, then it's all the tires that could have been made at some point in time. So the sampled population in this sense is considered infinite, right? Just because you happen to produce those tires specifically, you could have produced something else, right? And so now we have this kind of infinite idea. And so we can't really make a frame to draw from, but we have these 120 tires that they produced for this purpose. So of course that's our sample, but the idea that we could have produced any tire of any whatever is kind of mind-boggling. But let's talk about the differences between sampling from a finite population. So if you ever feel like you can define the entire population, now, no matter how big right? The population of Canada, we could potentially try to figure out what that is in one moment in time. Now that's really hard, right? But if we bring it down to maybe the college, right, we can look at and we can know it at one point in time how many students we have exactly. And we have student information on all those students, right? And so then we have this finite population. Whereas if we're looking at Canada, even if we're able to collect information on every citizen of Canada at one point in time, that seems kind of unrealistic, right? Making me think that it's an infinite population, just because there are births and there are deaths and there's changes all the time, and so to me that feels like an infinite population. But finite populations are way easier to deal with, because then we can kind of have them all and we could look at all of them, right? I like to think of, if you have to sample all the ants in the world, right, then it's a no thanks, right? Because it is essentially an infinite population. There's no way that we could sample all of them at the same time. So if we're sampling from a finite population, okay, so here, this is for a finite population, then we're going to be able to use a simple random sample. And there are lots of ways that we can generate a simple random sample, but as long as every individual in the population has the same probability of being selected into the sample, then you've collected a simple random sample. And of course, that's here. But a simple random sample of size n from a finite population of size capital N is a sample selected such that each possible sample of size n has the same probability of being selected. So I like to think of it as each individual has the same probability of being selected into the sample, but those are the same. Let me see if I can write that here. Each individual in the population. I guess I should have said each element, not necessarily an individual, which refers to a person, but usually we're talking about people. So each individual in the population has the same probability of being selected into the sample. Okay. So here I've got kind of the most basic way that we could collect a simple random sample. So if you have a finite population, then you would have some list of everyone, right? You would have a frame to pick from, right? And so all the students at Okanagan College, for example, right? We would go to the registrar's office and we could get, well, you can't, but if you had, research, whatever ideas, then maybe they would give, no, I don't think so. But in theory, we could have a list of all students at Okanagan College. And what we would do is we would probably have them in a spreadsheet somewhere, and Excel has a random number generator built in. It's fine. It's not the best random. It's not as random as it could be. There's random.org claims to be, or at least when I was working with it, I don't have to draw prize winners anymore, so I haven't done it in a while, but that's how we would draw prize winners, for example. So random.org was claiming to be the most random number generator. Of course, it's still built on an algorithm. There is still a computer that has to generate these random numbers. They're not random but they're as close to random as they can be. And so Excel has a built-in one, and that's fine, you can use that. And so what it does is it takes from a uniform distribution, right? So uniform means that every outcome has the same probability of happening, and then it generates a number between 0 and 1. You could multiply that by 100 if you prefer, but doesn't matter, right? Small decimals can still work with that. So what you would do beside each element or individual in your spreadsheet is you would assign them a random number, right? And so that spreadsheet could be organized, by student number, or it could be organized by last name or something, entirely different. So it is allowed to be organized, the initial list. So then when you assign a random number to it, then what you can do is you could sort it from smallest to largest, pick the first n, right? Pick the first 30 if that's the sample size that you want. You could sort it from largest to smallest, pick the first 30 there, or you could pick the middle 30. It doesn't really matter. At that point, they've all been assigned random numbers. And so you've lost any sort of information that comes from last names or student numbers and stuff like that, which you want to eliminate because they might introduce bias unintentionally. So once you've assigned a random number, then you can sort them and then you can pick whichever one you want. So here they're saying select the n elements corresponding to the n smallest random numbers, or you could pick out every 10th one. There are lots of ways you could do it. What's interesting is that the number of different simple random samples that we could have. So imagine you're taking a sample of size 30 from a population that's, let's say, only 1,000 people, right? Let's keep it nice and kind of reasonable. So now our population size is 1,000, and I want to randomly select 30 of those, right? And so let n be 1,000. It's a pretty small population, and I want to collect a sample of size 30. So imagine you go in, you collect a random sample of size 30, you put those guys back in, and then you shuffle them all up, you assign them new random numbers maybe, and then take a random sample of size 30, okay, collect their information, put them back in, and so on and so forth. How many times can you do that and have unique samples? Well, n factorial, that's 1,000 factorial. What's that? 1,000 times 999 times 998 times 997. Oh man, remember factorials? No thanks. Right, so that's going to be 1,000 factorial divided by n factorial. So in our case, it would be 30 factorial, and then times 1,000 minus 30 factorial. Just for a quick, let's see here. Let's see how many we would have. This isn't something that I want you to do, but it is good to know, right? How many possible samples could I be collecting here? It's going to be a large number, right? And so we have 1,000 factorial over 30 factorial over 1,000, or times 1,000 minus 30 factorial. 1,000 factorial. I'm not even sure most calculators have a factorial button. Right now, I'm not finding it. Come on. Ha, found it. It's in the second menu. I'm gonna see if it can even handle 1,000 factorial. Math error. Doesn't even want to do it. What's the trick? Well, you could write out 1,000 factorial up to 1,000 minus 30 factorial. That's still a large number of terms, so I'm not going to do that. And then you could cancel those out. And then you'd have 1 over 30 factorial. Well, not 1 over. You'd have 1,000 times 999 times 998 times 997. It's going to be huge. Huge. So many, many, many ways that we can collect random samples from a finite population, and never mind an infinite population. The reason I bring this up is because this is going to be the idea behind sampling distributions later on, right? And so sampling distributions are what we build our inferences on. So this idea of there being so many different types or different samples, even though they're randomly selected and whatever, that idea is going to come into play. Let's focus on this for now. So if we're sampling from an infinite population, right? So we can't possibly get a handle on this entire population. So then we're sampling from an infinite population. We can still collect a random sample, but we call it just a random sample instead of a simple random sample. And later we'll just call it a sample. We'll just assume that everything was randomly selected appropriately. Okay, but a random sample of size n from an infinite population is one where each element selected comes from the same population. And of course, that implies that it's the population that you're interested in studying, right? A lot of the time people miss the mark, right? They try to select these outcomes from some population, but it turns out that population that they're targeting isn't necessarily the one that they want to be talking about, right? And so from the same population, the population that we are interested in studying. That's implied, right? But doesn't hurt to say it. So everyone has to come from the same population, otherwise it's not going to work. We can't consider it a random sample, and each element has to be selected independently. So often if we're sampling from an infinite population, then just as long as our elements come from the same population, that's kind of a must no matter what. But as long as we can argue that each element is selected independently of each other, then we can argue that we have a random sample, right? Which would mean what? Which would mean that our sample is representative of our population, right? So here, as long as each element is selected independently, we can assume we have a random sample which means we can also assume that that sample is representative of the population, which means we can also assume our sample is representative of the population. That's a good thing, because that's the only way that we're going to be able to use the sample to draw conclusions about the population, right? And so everything's just kind of hinging on this. How did we collect our data? So there's kind of a fun example here. It's kind of wordy, but I'll give you the gist here. So for selecting a sample from an infinite population, if an employee is asked to select and interview a sample of customers in order to develop a profile of the customers who visit some restaurant, specifically a fast food restaurant, I guess, it doesn't matter. So customers, they come and the order that they come in, it's ongoing and everyone's just coming in whenever they want, right? And so we don't know who's coming in, and there, I'm trying to find my place here. So we don't know who's coming in, and there's no way to figure out a list of all the past, future, and present customers, right? And so now we have this infinite population. And so if we are sampling from an infinite population, we said, okay, as long as we're sampling from the right population, right, and all the elements are independently selected, then we can assume that we have this random sample. Okay, so as long as a sampling procedure is designed so that all the elements in the sample are customers of the restaurant and they are selected independently, right, then a random sample will be obtained. So in this case, the employee collecting the sample needs to select the sample from people who come into the restaurant and make a purchase, right, to ensure that the same population condition is satisfied. So they've got this example, if someone's just coming in to use the restroom but not buying anything, they're not considered a customer. And so then we shouldn't include them in our sample, right? So as long as we're selecting people who are making a purchase, then that first condition that says, okay, everyone has to be from the same population, so people who make a purchase at the fast food restaurant, is satisfied. Now, how do we make sure that customers are independently selected, right? So you want to avoid things like sampling from the same group necessarily, unless it happens, but they've got a couple of warnings here. So what we're trying to prevent is selection bias. Okay, so things like, well, people who come in the same group, they would probably answer the questions similarly, right? Often, not necessarily, but often. Right, and if you come in at the same time, then, and you're only looking at one time of the day, right, between 9 and 10 a.m. maybe, you're going to get a different sample than you would between 9 and 10 p.m. probably. I don't know. So, oops. Selection bias in this case is if the interviewer, which also happens to be an employee at the restaurant, seems really unfair. They're really going above and beyond for their job. But if they were free to select customers for the sample arbitrarily, so the interviewer might feel more comfortable selecting customers in a particular age group, or they might avoid other age groups, right? If they selected a group of 5 customers who entered the restaurant together, then they would see similar characteristics likely, which might provide misleading information about the population of customers, right? So these are all things that we need to keep an eye out for. So selection bias such as this can be avoided by ensuring that the selection of a particular customer does not influence the selection of any other customer, right? And so that's the definition of it being independent, okay? So in other words, the elements, the customers are selected independently. Here I'll say the selection of a particular customer does not influence the selection of another customer. This is the definition of independence. Yeah. Is that all I wanted to say about sampling? Okay, that's fine. Bring this whole chunk in here. So sampling is a big field. It's a huge field of study, and of course there are professionals who, and all they do is create sampling designs and survey designs and stuff like that, right? And so there's a lot that goes into it, but from here on out, we just kind of assume that we have a good sample, so a good representative sample. It was randomly selected, but we still need to be able to pick up on those cues where there might have been selection bias in our sample. And so our results are not as robust as they would be if we just had independently selected samples. So once we have our sample, then it's time to see what's happening in the sample. So after we collect, after we have collected our data, right? Or potentially it's just been collected for us, or it has been collected for us. We start looking at some of the characteristics of the sample. We start looking at some of the characteristics of our sample. Just as a little reminder, whoops, hey. Try to keep it on the same. There. Information from a sample is called a statistic, right? Or a sample statistic. But a statistic is information from a sample. So things like the sample mean, the sample standard deviation, those would all be statistics. I'll say, recall a statistic is information calculated from a sample. Information calculated from a sample. Whereas a parameter is the same thing, but it's calculated, it would be calculated from the population. Information calculated from a population. So we'll see this connection between, okay, there's a sample mean, but then there's also a population mean, right? And we're looking at the sample mean to try to learn about the population mean, right? And so that's inference. So we can go back and we can talk about inference in terms of statistics and parameters. So therefore, inference is taking a statistic to learn about its corresponding parameter. Taking a statistic to learn about its corresponding parameter. Okay. So for example, right, we might have a statistic and the corresponding parameter, just in its most basic sense. We have X bar is a statistic, that's the sample mean. Maybe I'll write that here. X bar is the sample mean. We would use X bar to try to learn about mu, right, which is the population mean. Okay. Same thing about S versus sigma. Right? And in this textbook, they use p hat or sorry, I can't even say it, p bar. It feels so weird. I typically use p hat, not p bar, but this textbook seems to like to use p bar, but that's the sample proportion. For me, anything with a bar over it is a mean, but guess not. So this here is the sample proportion. This is the sample standard deviation. Population standard deviation, and P we'll use, you could use pi, but it gets confusing because we have, the number pi, the irrational number pi, but this is the population proportion. And now I bumped this little blurb down so much, enough to remove it because I'm out of time, but have a read through those summary notes for a quick review of some of the stuff, and then we're just going to talk about it. There's not a lot that we're going to do there until a little bit later. So I think I'm out of time, I'm pretty sure. So if you have any questions, let me know. Otherwise, I'll see you on Friday. Yeah. Stop this recording here.